Okay, so this is the second new style lecture using a whiteboard. Um, it's going to be another 1 hour lecture. I just want to recap the main things from our previous lecture. They are basically, I think, if there's one formula that you need to remember is this one here. When we talk about an electron and we imagine it as the smallest superconducting loop, again, there's 2 points you need to make. One is it's not the smallest. Proton has a much smaller radius in the femtometer scale, not in the picometer scale. But it's the same principle. It's the ring current model of elementary particles, which goes back to Parson and Schrödinger and Einstein and Hendrik Anton Lorentz, who I'm a Belgian. What he says to me, especially in the questions, the discussions during the Solvay conferences, what he says speaks very much to my heart. Unfortunately, he died. His successor at Leiden, Ehrenfest, he committed suicide. So there's, I feel sometimes I'm building on elements that, these people did not have much time left to work on. But yes, a charge going around and around and around in, a loop whose radius is less than a picometer. Will acquire an effective mass, and that respects Einstein's relativity theory. There's 2 complications. One is really, the mass generating mechanism. Is there like a, we said this charge does not have an infinitesimally small spatial dimension. It's equal to its radius is the classical electron radius, the Lorentz radius or the Thomson radius, which is the fine structure constant multiplied by the charge radius or the quantum radius of the electron. So you may wonder, where does this effective mass come from? We have a mathematical model here. We know that the kinetic and the potential energy of an electron would be distributed over the kinetic energy of that Zitterbewegung charge going around and around, or I don't exclude some more complicated motion, toroidal, or something more like Schrödinger's orbitals for a hydrogen atom. The charge going through the center and then going to the other side. Not really going through the center and going through the other side. That's with lobes, with non-lobes. I think my intuition is, this basic model is right, and we don't need to make things more complicated than they are, especially because we are going to make them more complicated when thinking about this electron being in an atomic or a molecular orbital, where we will have rotations within rotations. So the question is, can we apply, this formula that the effective mass would somehow be equal to, the Lorentz factor times, how would I write it? The mass of the Zitterbewegung charge. I think the buck stops there. I don't think this formula can be applied. Why? Because we have measured anomaly in, then I go back to this one here. We have this mini superconducting loop, only one charge. It generates a magnetic field that keeps the ring current going. The ring current generates the magnetic field that keeps the charge going. But there's a magnetic moment which we can measure. It's a dipole moment. I said, it's pretty impressive in terms of the force that you calculate, but it's okay in terms of, we're not modeling some black hole here. When you apply, general relativity theory to it, there's nothing outrageous that is coming out. Just like there's nothing outrageous coming out from this equation. When you think about, we need to bring this down, there's no continuity, a point-like charge zipping around at the speed of light in a ring current is not exactly the same as having, some kind of a homogeneous current, or an analysis in terms of the Maxwell equations, in terms of charge densities. Nothing outrageous comes out of that, except perhaps for this, where you maybe think this Zitterbewegung charge has not only a finite spatial dimension, but maybe also some non-zero rest mass. Very tiny, yeah, because I said this model requires that we need to be able to accelerate it at a speed v, which is almost or very nearly equal to c. To accelerate it to c, really, it does require, just like a photon, that it has no zero rest mass. And the funny thing is, the Kodata value, the measured magnetic moment, for an electron is slightly larger than what we would get based on this, which is very weird, because the magnetic moment of something is the current times the area of the loop. So either the current has to increase, or the area of the loop has to increase. Both the area of the loop, well, the area of the loop is connected to the frequency. The area of the loop is connected to these mechanical velocities, radius. So perhaps we should distinguish between a theoretical electron model and a real electron model based on the assumption that this Zitterbewegung charge does not only have a finite spatial dimension, which, as we said, is a classical electron radius, or is modeled by that, the fine structure constant times this Compton radius. But we think there is no need for that. We don't think there is a need for a mass generation mechanism. We can think of a charge without having sort of a microgeon-like seed of mass. I'm getting ahead of myself and actually not addressing what I want to address in this lecture, which is basically like, how do you combine these equations into something that is more useful in terms of, electrons actually moving around in space and perhaps, hitting a positron and annihilating with each other, and how you analyze that in wave function math. No, we don't want to do that. We want to get at that lecture, and so this is the second thing which we ask you to remember from this first lecture, is that you can have a wave function representation, cosine, sine, is it really like the combination of two linear oscillators that are perpendicular to each other? You know, if you look at a star engine can have two pistons, three pistons, four pistons, five pistons, any number of pistons, and you know we can build a multi-dimensional oscillator model. Well, multi-dimensional in the sense that it's still going to give like a ring current, a nice circular motion, but you know, we're using Euler's numbers for the time being, Euler's formula, and so we're going to model these things in terms of a cosine and a sine that we combine with some phase, and we're going to apply indeed, you know, the Planck-Einstein relationship, which says basically, you know, in nature things are quantized, and so the physical action in one loop needs to be, you know, a multiple of h bar, because we're talking an orbital loop with h bar. It's the reduced constant. For photons, you can do a similar analysis, and you get rid of the bar on the h. But okay, that's sort of it, and probably you switched off now, which I hope you do not. If you did, then go back to this lecture and try to think about the main points, and then come back to what I'm gonna present now. I'm gonna check if it's running. Yeah, that's fine. It's the first time I'm experimenting with these like a screen capture presentation. So this is a lot of stuff. Let's bring it down again. We have the green thing. I'm using a red pen to make things come down, but we have a Zitterbewegung charge, you know, really the classical electron. I shouldn't call it that way. It's the Zitterbewegung charge, the point-like charge, which Schrödinger said should be there when you look at well, his own equation and Dirac's equation. And so that charge goes around, right, when it's stationary. And it goes around at the speed of light for a reason you might say logical or not logical. It's a charge without any attributes except the charge, you know, plus or minus the electron charge. And the electron as a whole is really made of this point-like unit charge for an electron or a positron going around in a loop that, you know, Einstein's mass energy and equivalence relationship, the Planck-Einstein relationship, and then sort of your classical, well, Newtonian formulas for centripetal forces and acceleration says it should be having. So we do have a perpetuum model. The perpetuum mobile is now, you know, we're looking at it, and as you know, we're a stationary electron. As soon as you apply some electromagnetic force on it, even it's very small, it's going to start moving, you know, this loop in this or in that, or, you know, in whatever direction in 3D space. The question of our reference frame is, you know, we need to bring things down. We need to assume this whole thing is going to move, you know, in some direction, which, you know, to facilitate the math, we are going to call the x direction. And so the y and the z direction, they are a plane, right? And that plane is going to be the plane of our call it imaginary unit I. You know, we have a lot of conventions in physics and mathematics in terms of, you know, left-hand rules and right-hand rules when designing your coordinate frames, when talking about the electromagnetic force, when talking about what mirror symmetry is, and all these kind of things. So we say that the our imaginary unit that's going to be a rotation operator now in the y and z plane. And the linear motion, any motion that is outside of that yz plane, we're gonna analyze it in terms of, we're gonna call it an x direction. And because we want to be clear and model the simple stuff situation, because this rotation, that this is what I point out here. A ring current, when you place it in a magnetic field, it's gonna have a precessional motion. So it's not gonna go like this. It's gonna go like this. It's gonna have a precessional motion. When you put things in a penning trap, this is the real trajectory, well simplified, of an electron. There's gonna be a secondary rotation which is linked to the precession motion. So there's a lot of complications. The main ones we put here, precession. The biggest one is probably, this thing. Likely, when you have a magnetic field, the oscillatory motion and its magnetic moment up or down. This thing is going to probably move like this rather than like this. So there's a lot of complications, but we're going to simplify stuff and bring it back to the very basic math that you need and want to explain the universe, well, or the electron. I copied here my main inspiration. This is a figure from a bunch of people who have been working on cold fusion and who are still working on cold fusion, and they came up with this what I call the the ultimate electron model. In normal circumstances, goes around stationary electron, but then we add some linear component to the velocity of our theta-beweging charge. What's going to happen is that for low velocities, the radius of this moment, quite mechanical, needs to become smaller, because what is happening is that you add, a linear component in the x direction to a motion that was only in the xy direction. And because the speed of light, the velocity, tangential velocity of that charge, when you compare it with its total velocity as a vector in the x, y, and z directions, if you increase the velocity in the z direction or in the x direction, which is what we are doing now, then the velocity in the y and z direction needs to decrease. So if the velocity in the y and z direction decreases because we are adding this x component to the velocity vector, then we get a spiral that has a smaller radius. And something is happening here. We have like kind of a new frequency, a linear frequency, rather than just the orbital one. And that gives rise to funny stuff, which is what I'm putting here. We can distinguish not only the orbital frequency, but also some kind of a linear wavelength, not only a radius, but some linear wavelength between all the crests here. And then we have the de Broglie wavelength, of course. Lambda is h over p, which behaves very funnily. If the momentum is 0, then we have a division by something finite divided by 0, and we get, an infinite wavelength. What does that mean? Or if p goes to infinite, all of the motion is linear, then this radius, reduces to 0. What really happens then? We have the Bruys wavelength here, or just put lambda. It's not a Compton wavelength. It's not this weird orbital wavelength linked to the orbital momentum. No, okay, it's just the Bruys wavelength. When the momentum gets infinite, you say it can't get infinite. We can't accelerate an electron to the speed of light, and you're right, we can't. But so you get an interpretation for the Bruys wavelength, which I put here, which basically is a weird formula combining Lorentz factor, this thing, and well, I'm just 5 minutes into my second slide, and I realize that once again I'm getting ahead of myself, and giving you a lot of conclusions or questions without going through the math. So let me go through the math. The phase of the electron, which we will multiply by I, right? That goes round and round and round and round and round. So we have some kind of frequency and we have the time. Now that we are looking at an electron that is moving, we need Einstein's special relativity theory, and we need to distinguish between, the inertial frame of reference for the electron, whether it moves or, goes in whatever direction. For the electron, if it would be a conscious thing, which of course it isn't, in its own reference frame, the inertial reference frame, the math is still the same. I am a ring current. I have, a certain frequency. I measure time in my reference frame through the cycle time. The time that it takes me to go through one oscillation. So we must distinguish like some kind of hypothetical wave function argument or phase factor, which is frequency measured in its own frame reference and a time that is measured in the inertial frame of reference. So the Planck-Einstein relationship is going to be very funny what I say. I'm going to show you that there's a way of thinking about the wave function argument as being a relativistically invariant. But the fundamental constants of nature, Planck's constant, electric charge, plus or minus, the velocity of speed, they don't depend on your reference frame, right? They are the same. So here it is exactly the same. We don't care about the reference frame. Planck-Einstein relationship in the electron's reference frame tells us this frequency needs to be, the energy of the electron, our electron, or whatever you want to look at, micro object, divided by h bar, the energy in whatever reference frame of some system is always equal to, I would say, a multiple, when we talk about atomic orbitals, a multiple of h bar times h bar. So that means that the frequency as measured in the inertial, we put a prime here because we are in our reference frame and we're, the prime is the reference frame of the stationary electron, and the electron is also stationary when it moves around, but that's only in our perception of things. So it's the rest mass. The nice thing that connects the reference frame of the electron and our reference frame is that we can both agree that the electron has some measured rest mass, which we know when we put it in an accelerator becomes a relativistic energy. or rest mass. Well, not a rest mass. The rest mass stays the same. But as it acquires kinetic energy, the energy of the electron will change from E0 to what I put in the other formulas here, EV. And the change in the energy and in the mass as we perceive it, as we apply forces to accelerate it in this or that direction, will change. And it will change with 1 divided by the square root of 1 minus the relative velocity, b squared. I'm outside of the frame there. Let me restore it. So there's a funny way of looking at things then, where you basically say like, okay, and the exposition of, we see these things moving around, the electron moves, and in our reference frame, it has a linear velocity. This has nothing to do with the v square is c. No, it has, it's 0.1 times the velocity of speed, which is, we would like to express it as a relative velocity against the absolute speed of light, times t as measured in our reference frame. No, this is x, this is v, this is t, this is not x bar v times squared. No, it's not. If it would be, then, because we may wonder, I'm cleaning up my screen here. If it would be, we do have an x bar, of course, but it's 0. In the reference frame of the electron, it just stays where it is. It is only in our reference frame that we now see an x position and some linear velocity, a vector in the x position, and in our reference frame, every micro or femtosecond, it is it's elsewhere. And the relationship between this 0 and our x is given by this equation. I hope we can agree till then. The funny thing is that we're talking motion. Motion is I wrote it in one of my more philosophical papers. The time goes in one direction only, and space is real. 3D space, 1D time. Time flows in one direction only. That's other nonsense I want to talk about. But yeah, when you talk about motion, things in motion, space, this is where the dependence comes from, and time, they're no longer independent. Actually, we derive our Kantian or Einsteinian notions of time and space, now Einsteinian notions from special relativity theory, which said like, if you look at position, if you look at length, if you look at variables like that, energy, mass, force over a distance, then something happens with the logical conclusion is that time is local. Time is local. The time as measured in the reference frame of this electron, set by its own cycle time, it appears differently in our reference frame. And the formula for that is given by the Lorentz transformation, where we say like, okay, the time, and we can interpret it as a cycle time, a t2 minus a t1. Oops. It's gonna be related to our time variable by this formula, where there's a certain linear motion, there's an x position in our reference frame, and there's a certain velocity in our reference frame. So all these variables, t, v, x, are variables in our reference frame, and they sort of all are related to this one variable, t prime, in the reference frame of the electron. I put some other relativistic equations here, which are gonna be useful. Relativistic momentum, so not Newtonian momentum, is a mass, of course, but relativistic mass, and it increases with velocity times your usual velocity vector. Indeed, as I talked here, this relativistic mass involves the Lorentz factor to relate it to the rest mass, which is a quantity. I think in whatever reference frame your reference frame is moving, mine is not. Through these formulas, we can go from one to the other. The rest mass of the electron is what it is. That's not relative at all. It's just like this is an important point. C, h bar, and the rest mass of a proton are not relativistic. The rest mass of a proton or an electron is the rest mass of an electron of a proton. And this is something nice. I'm saying it as a side, but they do appear as to be, as fundamental as constants, fundamental physical constants in these system of units as the other ones. The fact is actually the concept of 1 kg is now referred to. It's quite complicated to Planck's unit of action, and frequency of a photon, and so many things more. But it's not fundamental. The kg is not fundamental. The rest mass of a proton and an electron, those are fundamental. But in this model, we explain them exactly because we say, what is a particle? A particle is charge in some oscillation, in some really small current of loop. So kind of vanishes this, and the fundamental concept indeed becomes the energy, which you relate. We can add a c square here, and it cancels out, and we get the same formula. Let me restore the original. The basic point is that if we say like, okay, let's assume that an electron, we can represent it by something that goes round and round, Euler's number minus a phase factor, but we look at it in its own reference frame, and we use this I, this imaginary unit, to measure, how the phase changes, the angle. Then you get, this formula, and we must write the T prime as, per Lorentz formula, as a T minus a, what did I do here? Okay, yeah, as Vx, but x, is V times T, so we get Pt here, we had V squared times T divided by C squared, and then just the same thing as we had here. So this is actually how time dilation works. You will say this has not been very useful, but I think it has been, because it shows, when you look at this, you can call it like an envelope function. So we have, these things, time moves, goes around. This is a constant. This is the variable thing, and it's like an envelope function, which goes, it's equal to 1 minus beta square. It goes like this. The higher the speed is, this factor is going to go from 1 to 0. So that shows how time physically goes slower when we look at it and look at time in the reference frame of this electron that is moving. And this is the beauty about, the Zitterbewegung interpretation. It shows how these weird phenomena, time, time dilation, relativistic length, contraction, the radius of this thing, and it could be like this, or it could be, moving around at something. The radius of this thing, which generates mass, the mass of our electron, its radius becomes smaller. The clock starts going slower. And its mass, because the radius becomes smaller, we have also, less of a mass that is accelerated, and at the same time is being accelerated, giving, the total larger energy of this whole thing. But it shows, what length contraction, what time dilation, and the change of mass, relativistic mass, really is. That's very deep, and I'm sure I'm not doing a good job in trying to present it in half an hour. But that's what it is. I can rewrite, that's what I do here, to make things clearer or confuse you even more. The relativistic argument of the wave function in terms of what we can see, the relativistic energy, and we get same thing. What you see is that the 1 minus b square factors, they actually combine and reinforce this thing. The inverse Lorentz factor goes from 1 to 0. Well, the minus 1 b factor, b squared factor, goes from 1 to 0 even faster. It's just a quadratic function. If you were to extend it, would go down. So that all makes sense. That is all very beautiful, at the same time very deep. Let's go on to the next thing, where I'm going to talk about a wave function representation of this moving electron in actually much more detail. Well, I'm looking at this, and I'm going to pack it into a third lecture, because it's a lot of stuff. It's kind of nice where we want to get at, and that's where I'm going to encourage you to look at the next thing. Is we have an electron, right? Okay, but if we replace the Zitterbewegung charge by a positive Zitterbewegung charge, and then combine it with properties of something being having upspin and downspin, then we can make a kind of a special phase argument which combines basically time in our reference frame, the x position in our reference frame of the electron, and then we can play with the plus or minus signs of the imaginary units, and we have a presentation of electron and positron in terms of wave functions that are each other's complex conjugate. That's what I write here. Except for the fact that we have 8 theoretical possibilities: an electron going in the plus direction, in the minus direction, and in the spin up and the spin down direction. And we have only 4 phi. I think this is it's not a psi. not good at Greek letters, but we have the complex conjugate, but we still, have only 4 functions, actually 2 functions, the complex conjugate, to represent 8 physical possibilities. And that's not so good. So we are thinking there of, maybe adding an underbar, or it would be an overbar, in standard particle notation, but it's not so handy with editors, to represent, an electron and a positron moving in the plus or the minus direction with their spin up or spin down respectively by this wave function. And then the interesting thing is, can we then sort of add these, I don't call them amplitudes, I call them wave function representations of matter particles, and sort of see what comes out, for instance, when you have an electron and a positron annihilating each other. What happens with the charge? What happens with the electromagnetic field? And all these kind of things. So I will do that in the next lecture, because I said I feel this is going to get me into also what I want to talk about here is a wave function representation of a photon, where, with a photon we don't have particle, no. Let me clean up. Yeah, that's all the cleaning up I can do apparently. We don't have a charge. We just have an electric field vector, and we should always imagine that the, as this electric field factor goes up and down, there's a magnetic field factor also that, moves. So the wave function representation of a photon is a different beast, and I don't want to talk about that. I do want to talk about, matter particles, and I'm gonna do that actually. I present this slide very briefly to take sort of the same relativistic equations that we have here. An electron. Let me clean up the presentation as much as I can. Is going to have, the Lorentz factor times the exposition is going to relate to x minus vt. I said x in its own reference frame at 0. X we can replace by, vt, the linear velocity in a certain direction, times the t as measured in our reference frame. We have this relativistic formula which we presented already, the Lorentz factor times t minus vx over c squared. We have, very importantly, this sort of phase factor in a wave function representation of the electron in its own reference frame. And we are asking now, can we sort of write this in terms of, what we are interested in? We are now measuring, as we accelerate an electron in an electron beam, we are seeing that its relativistic mass is increasing hugely. We can measure it because that determines the forces we need to apply, the fields we need to apply to, get it to move even faster and give it more linear momentum p, so we can let it collide with its antimatter counterpart, or let it crash into I don't know, some nucleus or whatever. So yeah, of course we can do that. And then you get a very funny representation. We know that the momentum is equal to the Lorentz factor times zero rest mass times this velocity that we have, the linear velocity, linear momentum, linear velocity. We have our relativistic formula for, we have the relationship between energy and mass, basically. And then we have this one here. Let me think about, the velocity, of course, is the momentum divided by the mass factor. P is V times M0 is gamma times, so we have this equation, so we must have this equation. And then we have here that, of course, this M0 must be equal to the energy divided by c squared, because again, mass is just Energy, but energy in a special way. It's basically charge in motion with a c factor, that is the orbital velocity of the charge, the Titterbewegung charge, an electron of a positron. So what we get then is that if we take this equation, we have the 1 over h squared here, which we move out, E0 times gamma t, minus, we brought E0 inside, so we multiply it by gamma v x. E0 times gamma vx is pc square, we had that here, the x is still there, divided by E0, the E0 is there, and the c square is also still there. So it all works out. Let me clean up. We can scrap what we are doing here. The c square goes away, and we arrive at this beautiful equation. EV minus PX. Now this looks so much like what you've encountered when you were analyzing, a wave in a certain volume. Let's see, maybe E vector or B vector, where we say like we can analyze it in the position space. We can say at t is t0, the value of the variable, the wave function, the electric field vector is this. Or we can say no, we analyze it at some position x equal to x0 is when we go from some point in space x1 to some point in space x2, we see how it evolves. Sorry, no, we fix the space from some point time t0 to some point t1 or t1 or t2 is where we say like, yeah, well, we go through space and we will have a wave number that will, when we multiply it with the spatial variable, give us the value of the electric field or the magnetic field or whatever variable that measures the wave. So that's all very nice, and but it's a bit of an optical thing, and this is where the limits are of this wave function representation, and then I will talk about it in the next lecture. Yeah, I can't clean up anymore. Is that this is kind of artificial. We have t, we have a frequency, we have x, and we have a wave number. We will show that it's not a a Zitterbewegung charge that goes around and has some increasing. In this case, it doesn't need to increase, but it has some increasing linear velocity. It's a very weird trajectory, but at every point in time, we need to realize, at point 0, it's there, at time 0, it's there. It's not like, this kind of wave that was generated by, I don't know what, a radar or moving charge that moved for some time and created this thing. It's not. At any point in time, our Zitterbewegung charge is somewhere. It's like what Richard Feynman said, the charge is not some smeared out distribution of charge. Our charge is either here or it's there at any point in time. And so that means that it's not all over space, it's somewhere. Either here or there, but not everywhere. And this is the disadvantage of this wave function representation. And I will talk about that more because it raises big questions on, you know, how you would combine wave functions when you talk about, you know, these are two bosons, so we'll add the amplitudes, or these are two, sorry, fermions, or these are two bosons, so we know it's actually for fermions you have to subtract amplitudes, for bosons you have to add them. There's a lot of hanky-panking around there, and we think it's not realistic in terms of how virtual particles are used to sort of model the in-between states between the beginning, two stable particles that collide, and then two or more other stable particles that come out of it, light particles or matter particles, and then in between you have an S matrix, Spur matrix, with some temporary disequilibrium things that are happening, and then you're going to try to factor that, and you arrive at, you know, well, maybe a quark with these and these qualities is going to explain this, or you know, in gluons, or something else. We don't think so. We think a fundamental mistake was made, and it was made for a good reason. You know, the S matrix approach doesn't work for these reasons. You know, when you use a wave function approach to represent elementary particles, you need to realize it's something entirely different than using it for, you know, represent a photon. And so the dimensions are difficult and different. Not difficult, they are different. And then also, you know, the thing that we have, this sort of mechanical application of, you know, well, we're going to have a frequency in time, and we're going to have a frequency in space, you know, a wave number and a wave, well, frequency. We just call it the frequency, reduced frequency. It's not so easy. You know, what kind of frequency are you talking about? And then again, the basic problem is often that I think in quantum physics we tend to confuse the trajectory with what is actually happening, which is a charge going up and down, but always being somewhere at some point in space and somewhere in time. Xt or Tx, the time where the thing was when it was at position X, and the position where it was at point T. So we're talking functions, and a lot of classical concepts do not immediately transform into you know, quantum mechanical concepts. They make sense. We can work with them. We get fascinating stuff out of them. But yeah, when seeing the confusion on this screen, let me try to clean up. Apparently I can't roll back a lot of things. That's probably not great, but I said it's my second lecture. I'll soldier on. I will do a third one, and that's gonna be it. Yeah, that's me on the mountains. Okay.